In this presentation, I consider diffusion in ideal gas mixtures made up of three components, and I wish to demonstrate the possibility of uphill diffusion. The diffusion process is described by the Maxwell-Stefan equations that were put forward by James Clerk Maxwell and Joseph Stefan in the 19th century. This presentation is an abridged version of a video talk titled Uphill Diffusion that can be viewed on my YouTube channel. We now consider diffusion in ternary gas mixtures, and the objective is to demonstrate the possibility of uphill diffusion in such systems. We begin by formulating the Maxwell-Stefan equations to describe the diffusion in ternary gas mixtures. The force exerted per mole of species 1 is balanced by the friction species 1 experiences because of relative motion with respect to species 2 and relative motion with respect to species 3. Similarly, the force acting per mole of species 2 is balanced by the friction species 2 experiences in moving relative to species 1 and the friction it experiences with species 3 in view of the velocity differences between species 2 and species 3. In view of the Gibbs-Duhem constraint, only two of the driving forces are independent, and there are only two equations to consider. There are three independent Maxwell-Stefan diffusibilities, D12, D13, and D23. These represent respectively the inverse of the drag between 1 and 2, inverse of the drag between 1 and 3, and inverse of the drag between 2 and 3. D21 equals D12 as a result of the Onsager reciprocal relations. In setting up these equations, we ignore three-body collisions. That is the assumption normally made in the development of the kinetic theory of gases. The Maxwell-Stefan diffusibilities, D12, D13, and D23, are all independent of composition for ideal gas mixtures, and these can be determined with very good accuracy using the kinetic gas theory. An important advantage of the use of the Maxwell-Stefan formulation, say in comparison with the Onsager formulation, is that the diffusibilities D12, D13, and D23 are independent of the choice of the reference frame, because these diffusibilities are defined in terms of differences in the diffusion velocities, one with respect to 2, one with respect to 3, and 2 with respect to 3. The constraint imposed by the second law of thermodynamics demands that these Maxwell-Stefan diffusibilities be positive definite. The Maxwell-Stefan equations for the ternary gas mixture can be rewritten in this form using two-dimensional matrix notation. The column matrix J1, J2 represent the diffusion fluxes, and the column matrix of mole fraction gradients are indicated here. The constant of proportionality is the matrix of Fick diffusivities, and the elements of this matrix can be determined explicitly in terms of the three Maxwell-Stefan diffusivities D12, D13, and D23 that are calculable from the kinetic gas theory. Note, in general, that since these diffusivities are not equal to one another, the cross coefficients D12 and D21 are generally non-zero. The sign of these cross coefficients depends on how we number the species 1, 2, and 3. With a different numbering scheme, the signs of these cross coefficients may change. Let us present the calculations for the matrix of Fick diffusivities for a ternary mixture of hydrogen, which is component 1, nitrogen, which is component 2, and carbon dioxide, which is component 3. The D matrix is calculated at the composition x1 0.25, x2 0.5, x3 0.25. And from the kinetic gas theory, the Maxwell-Stefan diffusivities D12, D13, and D23 can be calculated, and the values are shown here. For the pairs D12 and D13, these are the hydrogen-nitrogen pair and the hydrogen-CO2 pair. The diffusivities are significantly higher than the diffusivity of the 2,3 pair, which is the nitrogen-CO2 pair. The Fick diffusivity matrix has a large and negative value for the cross coefficient shown here, minus 3.83, which is larger than the diagonal element D22, which has a value of 2.16. This implies the following. If we did a set of experiments in which the gradient of component 2, that is nitrogen, is 0, we will note from this matrix equation that the flux of component 2 is equals minus 1 divided by Vm times D21 times the mole fraction gradient of 1. It is not 0, even though there is no contribution of the term containing the mole fraction gradient of component 2. Therefore, uphill diffusion will be experienced for nitrogen in experiments in which we maintain the gradient of the mole fraction of component 2 as 0. Duncan and Tour in 1962 published a set of diffusion experiments conducted in a 2-bulb diffusion apparatus connected by a 2 mm capillary tube. The initial compositions in bulb A and bulb B are indicated here. Interesting to note is that the nitrogen mole fraction initially is 0.5 in both bulbs, and therefore there is no driving force in terms of mole fractions for nitrogen. At time t is 0, the stopcock connecting the two bulbs is opened and interdiffusion is allowed to take place. The equilibration trajectories for hydrogen and carbon dioxide in bulbs A and bulb B follow the classical exponential increase and decrease that is to be expected as the bulb compositions approach equilibrium. The continuous lines shown here and the dashed lines shown here are the solutions to the Maxwell-Stefan equations using the data on the Maxwell-Stefan diffusivities determined from the kinetic gas theory. The equilibration trajectories for nitrogen in bulb A are indicated by the red circles, and in experimental data for equilibration in bulb B are indicated by the open circles. It is interesting to note that despite the fact that the initial compositions of nitrogen in the two bulbs A and B are the same initially, the fluxes of nitrogen in bulb A and bulb B are non-zero, and this causes the approach to equilibrium in bulb A to exhibit a minimum and in bulb B to exhibit a maximum before eventually they equilibrate to the same compositions in the time interval between 0 and 6 hours. We experience the phenomena of uphill diffusion for nitrogen. And what is notable is that the bulb B has a higher mole fraction of nitrogen, but this continues to increase at the expense of composition of nitrogen in bulb A. In other words, nitrogen is being pumped from bulb A to bulb B, and the reason for this in physical terms can be appreciated if we note that carbon dioxide in bulb A is initially 0.5 and in bulb B it is initially 0. The drag between nitrogen and carbon dioxide, which is 1 divided by the Maxwell-Stefan diffusivity D23, is large, and therefore the friction between nitrogen and carbon dioxide has the effect of dragging nitrogen from bulb A to bulb B. At this time, we note a plateau in the compositions. So even though there is a large difference in the mole fractions in the two bulbs, the flux of nitrogen at this point is 0 because the concentration profiles show a maximum here. And beyond that point, normal behavior manifests, and the two compositions in bulbs A and bulb B approach one another to finally reach equilibrium at very long times. The continuous red lines and the dashed red lines represent the solutions to the Maxwell-Stefan equation using the data on the Maxwell-Stefan diffusivities determined from the kinetic gas theory. Indeed, in this paper cited here, Joseph Stefan anticipated the occurrence of uphill diffusion in ternary gas mixtures using a formulation that is almost identical to the ones we use to solve and obtain these calculated profiles. The experimental data of Duncan and Tour measured in the two-bulb diffusion apparatus is plotted in ternary composition space in the red circles denote the equilibration from the initial compositions to the final equilibrated composition. The green squares show the plots of the experimental data in bulb B as it progresses from the initial state to the final equilibration state. The continuous green and red lines represent the solutions to the Maxwell-Stefan equations. If the diffusion process is assumed to be uncoupled, in other words, the flux of each component is taken to be proportional to the mole fraction gradient of that component with a proportionality constant di that is independent of composition, then the equilibration trajectory would follow a straight line drawn by the dashed black lines. The serpentine equilibration trajectory is a signature for uphill diffusion and will be observed in several examples that will follow the slide. We ask ourselves the question whether the interdiffusion of the ternary gas mixture in the two-bulb diffusion experiments of Duncan and Tour violates the second law of thermodynamics because of the uphill transport of nitrogen. The second law of thermodynamics mandates that the rate of entropy production be positive definite. The entropy production for the ternary mixture is given by this expression where J1, J2, and J3 are the diffusion fluxes of hydrogen, nitrogen, and carbon dioxide, and these represent the gradients of ln x1, ln x2, and ln x3, where x1, x2, and x3 are the mole fractions. For uphill diffusion of nitrogen, this contribution of this term is negative. In other words, nitrogen consumes entropy. This is not disallowed because hydrogen and CO2 produce entropy at such a rate that the overall rate of entropy production is positive definite. This is a photograph showing the influx and efflux of passengers from a Mumbai local train that has just stopped at Dadar station. We have influx of passengers who want to get into the train, and we have efflux of passengers who want to get out of this train because Dadar is their final destination. Any passenger who is stationary and wants to remain in the train may be dragged out due to the drag exerted by the passengers leaving the train. So we could have uphill transport of reluctant passengers who want to remain on the train due to interspecies drag.